Okay, so let's actually title this section Fundamental Theorem of Calculus. So this is 15.4 out of our book. It's Fundamental Theorem of Calculus. It is the day you've been waiting for all semester, right? It says the word calculus in here. You're finally there. Okay, so we're going to define the fundamental theorem of calculus. We're going to talk about f as a function. So we're going to let f be a continuous function. On the closed interval from a to b. And we're going to let capital F be any antiderivative of little f. You should have truly grown so much in this course. Just think about the beginning of the semester, we talked about continuity. Are all of those things kind of coming to mind? What does it mean to be continuous? Do you know what an antiderivative is? Okay, we're going to say then, if we have capital F, again being that any antiderivative, we're going to say that the integral from a to b of little f of x dx, and this is called the definite integral, right? We're going to say to evaluate this definite integral, all I have to do is find the antiderivative, which, what are we calling the antiderivative? What notation? Capital F. So we're going to call it capital F. All I have to do is evaluate the antiderivative at b, so capital F of b, and then I subtract the antiderivative, capital F, evaluated at a. Okay, this can also be written shorthand notation, which you will end up doing. This will say, find your antiderivative, so that means capital F of x, and then you put this line next to it, which tells you you're going to evaluate it from the bounds of a to b. So we've discussed what the definite integral means in terms of the area under the curve with these rectangles. Now we can say if I'm going to find actually the definite integral, I'm going to find the antiderivative and I'm going to evaluate it at these bounds. I'm going to do f of b minus f of a. And so these two things mean the exact same thing. Okay. All right, so let's actually do one similar to something that I had on the board here a moment ago. We're going to start it off pretty basic, and we're going to find the answer to the definite integral evaluated from 1 to 3 of the function 3x squared dx. Okay, you should be really comfortable with finding that antiderivative. Before, what you would do is you would find the antiderivative and you would put what on the end of it? I see, but now we have these bounds, and so we are able to actually evaluate and find the definite integral here. Okay, so help me out. What's the antiderivative of 3x squared? Yeah, you already did it in your head. You said I added 1 to the exponent, it makes it x cubed, and then you divided by that 3, so they canceled out. Okay, my notation though, I'm going to evaluate this from 1 to 3. So we do this in 2 steps. First showing that I've taken the antiderivative correctly, and then I'm about to evaluate it. And so then all I do next is I plug in which value first? 3. It says start at that far endpoint. We called it b. So I'm going to plug in and find 3 cubed. All right, I'm replacing where the x is with 3. And then I'm subtracting 1 cubed. And so you're going to get what? 26. Okay, great. Not so bad. Okay, we're going to, of course, like make this a little bit more difficult, but before we can do that, let's talk about some things that we can do, some properties of our definite integrals. So we are using the fundamental theorem of calculus. Let's see how we can use some properties. So properties of definite integrals. Okay, our first property. Relate this to finding that area under the curve. What if I said find the area under the curve from A to A? So that's like saying I have a definite integral from the boundary A to the boundary A of a function, let's call it f of x. What do you think the answer is? It's 0, right? I've gone nowhere. I mean, look on the board. If I said find the area under the curve at A, the answer is 0. Good. Okay, this next property is something similar to what we've already seen, but now we're talking about definite integrals. So let's make our bounds from A to B. We'll use k to represent a constant or something that's being multiplied a scalar. And so we'll have k times the function f of x. Don't forget you need to have dx written here. And then what have we been doing with the k? We've just been moving it to the front, right? We've been saying, let's move it to the front. We'll work out, find our antiderivative, and then multiply that k later. So yes, it's the exact same thing. We can do the same thing with our definite integrals that we could with our indefinite integrals. And so likewise, that brings up the similar property where we talk about seeing multiple functions, like we can call them f and g, and perhaps they're being added or subtracted. So as soon as I start writing this, I guarantee you can finish it on your own. So I'm saying now I've got bounds from A to B. I have a function f of x. It's added or subtracted to another function g of x. Finding the antiderivative with respect to x, so I have my dx here. And what do you think I'm going to do here? I'm going to break it up. I'm going to say I can evaluate the definite integral of f, and I can add or subtract it to the definite integral of g. So that's correct. I'm going to break it apart, essentially. It says I can look at little pieces at a time and then put it back together. Okay. Watch your notation, because I've mentioned before it's like a proper sentence. I have to have all of the parts to it. I have to have my integral, my integrand, and I have to have the variable in which I'm taking the antiderivative with respect to. Okay. The next one's kind of interesting. We didn't have the opportunity to see this one until now. Let's talk about going from A to B. We're going to use f to be our function again. And I'm looking over at the board where we said we were talking about, let me move this up because I've got a few people struggling to see it. Is that better? Okay. All right, let's, I arbitrarily called these endpoints A and B, but there's stuff in between here, right? Okay, so maybe something in between doesn't even have to be right in between. I can call it C. If I want to find, let's relate this to the area under the curve. If I want to find the area under a curve from A to B, I can break it up into, we just talked about, maybe do this portion and then add it to this next portion, and then I can add it to another portion, right? Okay, so I can break this up as many times as I want. And what this next property is telling me I can do is, let's say there is something I call C in between. I can rewrite this integral as saying I'm going to go from A to someplace in between. Let's just arbitrarily call it C. Find the antiderivative of the function f. And then I'm going to continue, and I'm going to go from C to B. So I wanted to evaluate the antiderivative from the bounds a to b, but I can break this up. I can break this up as many times as I want, actually. Okay, one last thing, number 5. The integral from a to b of f of x dx is the same thing as the opposite of the integral evaluated from b to a of that function. Okay, so what's different from the left and right hand sides? The order in which you're evaluating, right? And so you can see they're opposite in sign. Okay, so just kind of some properties to keep in mind as we go through. Let's see how well we remember our antiderivative rules and perhaps even U-substitution today. So we're going to find each definite integral. When you take notes and it's theorems or properties, you want to make sure that's a page that's easily accessible, because you're going to look through every problem that you work in your homework or examples, and you're going to refer back and say, which one of these properties can I use? So make sure that's someplace you can turn to. And then your examples are good, but you know that they gradually get more difficult. All right, find each definite integral. Let's take from 1 to 3. And our function will be 4x minus 2e to the x plus 5 over x So does this look like a function that I can just use those basic antiderivative properties, find the antiderivatives, and then what's the only added piece that we haven't been doing before? Evaluating at the endpoints, right? Yeah, okay. All right, so help me find the antiderivative. So the first thing we want to do is find the antiderivative of each one of these. Could I break this up into 3 separate parts? Yes, but is it beneficial at this point? No. So I can just take the antiderivative, and then I'm going to evaluate from 1 to 3. Okay, so give me the antiderivative of the first term. What was it? 2x squared, okay. You guys agree with that? You added 1, you divide by it? Okay. What about the negative 2e to the x? Yeah, the antiderivative of e to the x is e to the x. That negative 2 is going to go along. What about this last term, 5 over x? So it's 5 times 1 over x. The 5 is going to hang out. Should I know the antiderivative of 1 over x? Natural log of the absolute value of x. Good. And if this had been in the previous sections, I would go, okay, plus my constant, right? Okay. But now I'm finding the definite integral, so my notation is going to tell me I'm going to evaluate this from 1 to 3. This is what fundamental theorem of calculus said. And all I have to do is evaluate at each endpoint, right? And then subtract in the correct order. So what do I plug in first? And here's where you're going to need your calculator. If you haven't been using it much, you're going to want to pull out your calculator and make sure. Because it's going to ask you, whether it's on my exam or a quiz or my math lab, it'll say provide an approximation, or rather approximate it to the nearest tenth or whatever decimal place. Okay, so what I'm doing is I'm plugging in which value first? 3, okay. So I evaluate it at the far end point. So I have 2 times 3 squared minus 2 times e to the third. I'm trying to change color here. Plus 5 times the natural log of 3. And then I want to show my work, because it is very likely with 50 terms that I'm going to mess up in my calculator. So if I want to convey and communicate that I know what I'm doing, the next most important part for me to show is what I'm actually doing prior to sticking into the calculator. So what should I have in this next line here? I'm subtracting what? 2 times 1 squared, right? Is that what you said?
Yeah.
Okay. And I'm going to plug in 1 elsewhere. Any comments on what this, anything I need to do? As I have it written, is that correct?
With the signs, because you're subtracting.
Yeah. So can you say that louder?
The signs change because you're subtracting the whole base.
So remember it says to evaluate your functions at the far end point, in this case which is 3, and then subtract what you get when you evaluate at 1. So I actually need to either denote this with I am subtracting the quantity, or as you just mentioned, I can flip the signs, right? Okay, but somehow you need to make sure that you understand you're subtracting that whole function evaluated at the endpoint 1 in that case. Okay, so I'm going to go through. I'm going to have, what is that, 2 times 9 is 18 minus 2e cubed. Okay. And you pull out your calculator and you check yourself 3 times. And let's take it out to the thousandths place. All right, so any questions on that one? Negative 13.241. So we're doing the same things that we did in previous sections, but now we're actually evaluating. So if you think about all the concepts that you are going through in this course, every bit of this is dependent on some knowledge that you had, like evaluating functions, right? You learned that a long time ago. Now it comes into play here when you're doing calculus. So everything kind of comes together. Imagine how far you have come. Some of you guys came in and you're admittedly saying my algebra is so weak. Think of how well you did and improved with your algebra skills. So remember, all of these things come together to be able to work out a calculus problem. So you really have to be very careful on each step. Yes? Still see it? Yeah. Okay, definite integral. Let's look from 0 to 1. And we'll have 2x squared times the quantity 2x cubed plus 9 raised to the 6th, and we have dx. Okay, so once you have that written, I want you to start like talking through the mathematics with me. Okay, what did you think before you went straight to where we're going? What's the first thing you're going through in your head? Can I just add 1 and divide? Can I rewrite this in some way? Can I multiply this out and just use plain rules? That's the first thing you thought of. But you've done enough homework where you recognized I have a quantity to a power, and you thought I need to use U-substitution. So perfect. Okay, that's what you should be thinking. If you're not thinking the same thing as those guys, you need to do some more homework, or go find examples in the book, or come ask me. Okay, so U-substitution, I like it. What's our U? Okay, our U is going to be that quantity 2x cubed plus 9. Tell me what I have to do next. Find the differential. Okay, du is 6x squared dx. That's right. Okay. Now what? Everyone with me on this differential? I took the derivative of 2x cubed, so I multiply 3 times 2 is 6, subtract 1 from the power, and then you have to make sure you have dx. You with me on that? Okay. The whole purpose of U-substitution is to be able to substitute back in and be able to have this beautiful derivative or antiderivative that you can take based off of basic properties. Okay, so I go back up, and I want you to be careful on a few things. I'll warn you as we go. But you're already thinking, and just to be clear, my bounds are in x terms, right? But everything else is going to u in a moment. You have 2x squared dx, so I'm going to take an extra line here for a moment and just rewrite in some things that aren't really necessary for me to go through the problem, but to make sure people are looking at. You see how I reordered it? Okay, so you're already saying I can put in a u. It would be u to the 6, is that correct? All right, I'm replacing. Okay, and then I want to have everything in terms of u. So, oh, I lost my square here. Did y'all see when I rewrote it?
Yeah.
Okay, make sure. Okay, what do I do? So, if I want, I can move that 2 here, can I? You could take out a 3 like you're saying. That means you could do that. There's some people that wouldn't be as comfortable. Did you guys see what I did? All I had to just move that 2 to the front. Okay, so now this kind of feels a bit more comfortable because I want to turn the x squared dx into something that involves du. So what do I need to do here? So I want to be able to replace x squared dx. So over here, do I have an x squared dx that I can isolate? And so some of you guys were telling me to do what? Yeah, so I'd have 1/6 du. Now you said it right, divide, is x squared dx, right? So I don't want to have x squared dx in here anymore. I want to talk about taking the antiderivative in terms of u. So I'm going to replace the x squared dx with 1/6 du. Okay. So I have 2 times the integral with the bounds in terms of x from u to the, or of u to the 6, and what do I have in place of x squared dx? 1/6 du. Okay, is anyone starting to like to move those constants to the front? Okay, so I'm just going to rewrite this again. So this would be 2 times 1/6, which is 2/6, which is 1/3. Okay, so I've now have an integral with x bounds. It's 1/3 times, and then I'm going to take the antiderivative of u to the 6th du. What's the antiderivative? Okay, so I'm going to add 1, and I'm going to divide by it or multiply by the reciprocal, correct? We used to have plus the constant, but now we have bounds. You notice I've been very careful this whole time to keep them as x. I could convert those x's into u's and determine what the u value would be. I can do that. I don't think our book does that in your Help Me Solve This. So I'm going to be sure to indicate I'm still working in x's and I'm going to go back to x's. Okay? So I've got, sitting in the front, 1/21. I look back at what did I define u to be? So I've got 1/21 times the quantity 2x cubed plus 9 raised to the 7th. And I'm going to evaluate it from 0 to 1. Do we all agree with that? I'm going to pause it. Okay, so that sounds right. 700,200. Look how many of you guys got that. Same answer. Everyone okay? Any questions? You must realize that you will have to take your exam with a calculator. Like a lot of what we have done this whole semester, it's been verify with your calculator, show me all your work. You're still going to have to show all your work, but it's going to be very important to have your calculator to complete the computations. You absolutely have to have a calculator. I don't know the policy as far as the Learning Center and getting one from them. Okay, let's look at the next problem. And I'm going to give you some time to work on this one because that way I can walk around in this classroom setting and see where we are and if anyone has questions. Okay, so we're looking at a definite integral from 0 to 5. We have x divided by the quantity x squared plus 10. And I want you to spend a few minutes thinking about, is there anything I can do or what might I have to do? And then kind of go from there. I'll help you as I can. All right, so what you may have done is looked at it like this, or you may have said it was x squared plus 10 to the negative 1 times x dx. All these things are okay. So you try to work through and you said, I'm going to have to use U-substitution. You made your u that quantity. You found the differential. And you went back and you tried to substitute in for your u. So you would have a u to the negative 1, which I'll make a comment about that in a moment. And you said, I can't have u's mixed with x's, so you had to do some substitution here, right? And what's that substitution? It's going to be 1/2 du. So we should have everything in terms of u. And I saw that on most papers. And then what you should start getting more comfortable with is the idea that this scalar, this 1/2, can move to the front. And the only thing that I really take caution on, the fact that we had used the quantity raised to that negative power, is that sometimes we are tempted to add 1 and divide by it, but really u to the negative 1 is the same thing as 1 over u. And when you see it like that, that should trigger an antiderivative right away. And what is the antiderivative of 1 over u? Yeah, it's going to be the natural log of the absolute value of u. So here I have my 1/2. I have the antiderivative as the natural log of the absolute value of u. And then I'm going to plug in my endpoints using that fundamental theorem of calculus. But these are in terms of x's. So the last step that you have to do is make sure that everything is in terms of x. So you go back in and say I have x squared plus 10 here. And I'm going to evaluate now from 0 to 5. And so you plug in which x value first? The 5. Was that 35 then? Which is 35, okay. And this would be 10, right? You can use some rules of logarithms to make this easy to type in, but you don't have to do that. You get your calculator. You guys remember those properties of logs from before, those power rules? And okay, you could use those, but that's a little bit nerdy. We don't need to. What does this come out to be? And so let's go out 3 decimal places, so approximately 0.626. Okay.
Where'd you get 35?
Get this next little piece. Back to what we said earlier. So we're going to build up and start a little bit here. If I asked you to find an area under a curve from A to B, you should be able to write a definite integral. Let's say this function is f. And I said, please, for the sake of knowing the concept, tell me how to compute this area, find this area. What would you write with the definite integral? So you could say the area under the curve can be found by, and I'm not talking about that limit definition with the summation. I'm saying you should understand by the end of today that this is just the definite integral from a to b of our function f dx. Do you guys agree with that? Okay. The only thing is what we've been showing you guys are functions. Really, I've been showing you in the first quadrant, but it's been in the first or second quadrants. And so that area has come out to be positive. So if, I'm going to put a little dot here, if our function values are negative or equal to 0, then when I try to compute that definite integral, and I'm going to rewrite it, it will be negative. Okay, so we've been looking at things in the first quadrant, really. I would get the area under the curve just fine. But as I start looking elsewhere, I have to be aware that I'm going to get negative values. So let's just build up in the next 10 minutes an example. Let's take f of x equals x squared minus 4. And this will be our first example to show what we're talking about, because now we're actually going to compute areas under the curve of functions such as this one. So do you guys have an idea of what this function looks like, just based off of college algebra or any prerequisite material? It's x squared minus 4. What does that graph as? It's a parabola. Do you know anything about like vertex or how it was shifted? It was shifted down 4. Okay, so we could actually do a nice little sketch here. And I can place on the graph that vertex as 0, 4. And I should be able to place also the x-intercepts. Right, my x-intercepts would be what? Yep. 2 and negative 2. Okay. And so we're going to have a graph that looks like this. And that doesn't take a lot of effort. I get a calculator that I can quickly verify some things, right? But this is pretty nice. So let's say I want to find the area between, and I'm going to see how I have it written here. Let's look down here. Let me shade this in a color. Let's say I call this region A. So let's find the area for region A. Can you help me set up that integral? So it's area under a curve. What do I need to have for my boundaries if I'm just talking about this region? So you're taking the x boundaries. This first x boundary is, you said 0. And I'm cut off that region here, so it goes from 0 to where again? 2. I have the function defined as x squared minus 4. Can you quickly give me that answer? So I understood. If I'm looking at region A, it's bound from x equals 0 to x equals 2. Is that clear on how to set up definite integral. I was given a function. I know how to take the antiderivative. I learned the fundamental theorem of calculus, so I know how to plug in my endpoints. We said when I plug in 0, the function just evaluates to 0. So then all I did is I plugged in the 2. I got 8/3 minus 8. So I got, hopefully you got the same thing, negative 16/3. Okay, but what did you notice about your answer? You got a negative. Okay, if it actually wants the area, is that an appropriate answer for my area? No, so what are you going to do? You're going to take the absolute value, aren't you? So my area for that region is going to be 16/3. Okay. So if I were to ask you for the area from 0 to 5, you're going to have to look at where is it below the x-axis and where is it above. So let me actually have us do that next part. Let's have it go all the way out to 5. And I don't know how we just did that. Jesse, I jumped to an entire different day. Okay. Can I draw what my region B would look like? That's what I'm going to call this. I can continue my graph until these intersect. I have to scroll up a bit. But if I asked you to do region B, is my answer going to be positive or negative? It should be positive. Okay, so I'm going to leave that. We're going to finish this up next time. But the biggest thing to take away from this portion is making sure